In this video, we're going to consider a repairable system analysis in Weibull++. So if we go under the repairable system folder and we right-click, we have three types of analysis available. We have a non-parametric RDA, a parametric RDA, the RDA is recurrent data analysis, and we have event log. Event log is like a register of failures and repairs on a system. So we're going to consider the non-parametric RDA, but we already got one analysis being created, so we don't need to populate the sheet. So we open up this analysis, and we have three columns. We have a system ID where we've inserted two systems, system 1 and system 2. Then the second column tells us whether we're dealing with failures. So we're collecting essentially failures, and the last letter, the last reading for each system, it's an end reading. So it can coincide with the last failure, by the way. And then in the third column, we have the calendar data. So say, for example, for system 1, the first failure occurred at 281 hours. The second failure still for system 1 occurred at 336, and so on. And the same thing is repeated, obviously, with different numbers for system 2. So we don't have any information regarding what actually failed on the system because we are not doing a live data analysis, nor we are constructing an RBD on that. So it's a very synthetic type of analysis on our system of all the events, all the failure that occurred on our system. Once we've done that, we calculate, and we notice that because this is a non-parametric type of analysis, we do not have a quick calculation pad to extract numerical data. But we can extract numerical results. So we click on these three dots, and the numerical results represent the mean cumulative function. The mean cumulative function is essentially analyzing the two systems, can tell us what is the mean number of failure that we are expecting after a certain time. So if, for example, after 1,000 hours, I'm sort of expecting about 8.5 failures. And we have a lower limit and an upper limit, and we've also got a variance of our data because we have an analysis of two systems. So in fact, we can calculate the confidence band because we got multiple systems. If we only had one system, then we wouldn't be able to calculate the confidence band. But the more important things that we can get is the actual plot. And we only got one plot, and is the mean cumulative function. So again, is the number of failure, the mean number of failure among the two systems that we are expecting up to a time, say for example 1,000 hours or any reading, and is given by these discontinued blue lines, and the red line represent the upper limit and the lower limit. What we've done onto this plot, we have superimposed some trend, some black line to indicate different types of behavior across our population over time. So we have quite a steep trend at the beginning that marks our system is deteriorating fast, and followed by a decrease in the slope of our line, and which sort of would suggest that perhaps the effect of maintenance or some activity are having a beneficial effect. So say, for example, we're going from roughly 9 failure, 8.59 failure at 1,000 hours to only 12 after 3,000 hours. And after a certain time, say, for example, about 3,800, the system experience wear out. And we can see an increase, again, we can see an increase in the slope of our system. So we don't have, so we are in a context of non-homogeneous Poisson process, is a repairable system, and we don't, although we have a shallow line here, we don't get into a sort of homogeneous Poisson process. We don't have a sort of constant rate of occurrence. By the way, these black lines represent the rate of occurrence of our failure. But we can also view it in a sense as a sort of buffed up curve, because we have the first part of our data represent a high number of failure followed by a relatively flat, if we assume that this increase of three failures as a mean cumulative function represent roughly a flat, followed by again a steep increase in the number of failure. So the mean cumulative function, the graphical or the mean cumulative function, gives us a lot of useful information, although it doesn't give us a lot of numerical data apart from the mean number of events that we are expecting at the time, but it gives us the trend of the line, which is actually very important to understand whether, say, if we compare different populations, how compares one against the other. Or if we compare the effect of repair on one system, how the effect of repair actually manifests in a change of slope on our graph. So this information can actually be very useful for the practitioner, and they are very easy to compute with a relatively contained number of data points. Thank you for watching.